Assume everybody else can see. Okay, so we'll start. So this is UCL Chemical Sustainability Lecture Series. This is week 9, and I'm one of the co-organizers of this sustainability lecture series. So I thought I'd give a talk. It's been a long time since I gave a talk to UCL Chemistry, and this is also being viewed by people internationally as part of the Upsign network and others who have got linked through LinkedIn and other things. So welcome you all, and hope we have a chance for some Q&A, and I will keep an eye on the time as well. So so really what this talk is about is what I've discovered in the last 5 years, and a lot of it's not published. Actually, it's more about the philosophy of how we are now discovering and making materials, and it's a distinct difference to how, in particularly in reference to battery materials, it's distinctly different to what's going on in Asia. And I think it represents an opportunity for the UK to make batteries differently in some applications, particularly around solid state batteries and around high power batteries, where there are certain requirements for materials. But the headline figures I will give you in one of the slides in a minute. And so the emphasis on green manufacturing. And if you said, oh, well, you're a green chemist. Yes, I'm a green chemist. I'm interested in green chemistry. That's why I'm using water for a lot of our reactions, all our reactions. But a lot of the things to do with low energy manufacturing have just kind of happened, I wouldn't say by accident, but there have been fortuitous discoveries. And if you don't look at the rest of the talk and you just focus on one slide, this is the slide to focus on. So what are the key themes? So we're going to talk about materials discovery, how we can make materials, and it's really important to consistently make materials. One of the most exciting things, and this is the first time that I'm speaking about it, is about how we are now able to tailor defects in cathode materials I'm going to talk about using flash heating. And this is definitely something that I think, well, we've just patented this, and I think it's pretty different to what's been done before. So it's a new contribution to the area, which will surprise people. And our whole ethos is about bottom-up, intimately mixed elements that can give you consistent quality, and this allows you to compare properties between materials. So we're also about bottom-up in terms of overcoming mass transfer limitations. So we don't do shake and bake, we just do the cooking, but not the grinding. Time versus temperature is key. So optimizing materials, it appears that time versus temperature is controlling that, and understanding that in every material set is really key. And then, you know, how can we scale up using orders of magnitude less energy to get similar or better materials performance? And that's something that I'm definitely going to show you about for the first time today. Doesn't worry about the contents. So one of the things that I'll just highlight is my my journey, and my journey has been in different subjects: molecular precursors and chemical vapor deposition as a postdoc, PhD in synthesis, getting into supercritical fluids in the late 90s, and designing my own flow reactor from no knowledge whatsoever and just reading papers and trying to work it out with a bit of help. The use of supercritical fluids in other areas. And really, as I've progressed throughout my career, I've been really obsessed with manufacturing, which is not something I understood as a young person. I didn't really realize my true ambition was to get into manufacturing of materials and engineering. I was just thinking straight chemistry as an undergrad. So it's really amazing how journeys can sort of develop, and you really understand what you really love about the work you do. And I think what we're doing now in the battery area, I'm kind of, it's taking all of the experience I've had before and putting it together, really, which is what's exciting. And I've also had other roles around commercialization. And I also founded a charity called Upsign that supports people from British Pakistani backgrounds, both in the UK and overseas. And I'll talk more about that later. So we all are aware of the fact that there is a huge issue at the moment around sustainability of elements. Materials discovery allows us to perhaps swap out elements for other elements that might offer advantages. If you take batteries, the one that everybody talks about is cobalt, and mining of the Congo using I'd say unethical labor practices perhaps. And so there's a great sort of dilemma between the fact that we need cobalt for our cathodes and the NMC family, for decarbonizing transport, but how are we, squaring that with the ethical considerations of how it's mined? So there are many other elements that we could talk about, and this is a nice thing from, I think it's from, oh, I've forgotten his name now, it doesn't matter. Anyway, you can look this up. Okay, so David Cole-Hamilton, that's what I was thinking of. So our unique approach. So what, if I was to summarize all of the different ways in which we make materials, there are sort of three categories generically. One is we can directly make ready-to-use nanomaterials straight out of the bat, directly in a process. The second way is where we make nanomaterials as bottom-up precursors, and they are then converted via some kind of heat treatment. And as you're going to see, some of the heat treatments are very fast indeed. They're down to seconds or minutes potentially. So these heat treatments are giving a lot of control as well. The third type of thing is where we use a nano precursor that we've made, and we then add something to it. It could be a coating or something. It could be mixing with a lithium source. And having good mixing of these elements still at the sort of nano submicron level allows us to make bulk materials without any grinding. And so this is particularly on all the lithiated materials. Pathway 3 is the key one when you talk about anything that's lithiated. Pathway 2 could be used for non-lithiated materials, of course. So let's think about pathway number 1, direct synthesis, what our group is known for. I'll go through this a little bit quick because most people know what our group does, but I'll just sort of get to the main points. So we can directly make nanomaterials in flow reactors, which is the mixture of supercritical water, very hot water, and metal salts. And those metal salts can be different ratios of elements in there. And you can, do within less than a second, you're converting from the solution to a solid. This gives very homogeneous mixing. So this is a great nano precursor that you can use for solid state reactions. And so there's very short reaction times. This is actually more the diagram of the design. In other words, we're not just mixing metal salts with superheated water. We're actually sometimes adding some base to increase yields in the reaction. So this is pre-mixing in a cross piece or a T-piece, I should say. And then we have this thing called a confined jet mixer, which is patented by our group. I'm one of the inventors. And this is essentially the mixing of very hot water with this cold feed of metal salts or room temperature feed. And this is what gives a turbulent mixer with a high Reynolds number. And very, and is a continuous process. So you're continuously, after inline cooling, harvesting this slurry of particles in water. So it's a nice, safe way of making nanoparticles. And in our group, we've developed these flow reactors, not only in the pilot plant, which was, I think it was commissioned around about 2010, 2011, but we have this thing called high throughput mode, where we can introduce, tens of different elements sequentially into a process and make sort of phase diagrams, as is shown in this diagram, or we can go to the lab reactor. But you can go from the high throughput mode to the lab reactor mode, where you might make up to 200 grams of material, and then to the pilot plant, or you can just go from high throughput mode to the pilot plant. Flow reactors are very scalable, and I could talk about that if you're interested. And of course, we've covered a diverse range of materials over the years. So, that's just a gratuitous, that's what we've done slide. And in the basement of the Christopher Ingold building is our pilot plant, which we can make kilograms per hour of this. Very unusual for a university to have this kind of thing. It allows us to work in projects which include industry and Innovate UK type projects, where you're generally making prototypes and demonstrators. If you're interested more, this is a great review that we wrote in 2017. I strongly recommend it. It's a great introduction to the properties of water and the kind of materials. And it was really written as an introduction for anybody who wants to know more about this process. We're always interested to talk to people about collaborations. If people are interested in making materials, do come and talk to us. So let's talk about this unique approach and how we've been using it. So let's look at the other, some examples of part 2, where we're going to look at this making nanoparticles and then applying a heat treatment. And generally what happens, if we think about the top here is what I call slow precipitation. So in slow precipitation, this is sort of room temperature precipitation. The bottom diagram, part of the diagram, is what happens in continuous hydrothermal. So in the top part, you're generally making, you're mixing things together. So this could be a precipitate, or it could just be a solid state reaction where you take two oxides and you try and mix them together, and then you're doing shake and bake. Or it could be a precipitate where the elements are segregating because it's slow precipitation. So you may have an area that's nickel rich or cobalt rich because the precipitation was slow, and they have different rates of hydrolysis. And what happens is the orange area is the product. Normally, the first time you heat it, the reaction happens at the interface, and you've still got a lot of unreacted material, which is not fully reacted. So you then do a grinding step, and then you do another few heating and grinding steps, and eventually you get to the product. And the product might have some large particles because you heated it many times and you ground it many times. Our philosophy of bottom up is to say, okay, these two elements, the red and the blue, if we can make them in an intimate mixture, either a solid solution or as a few nanometers cross section of those particles, of those individual oxide or solid solutions, then there is no need to grind them, because each one of these blue ones has a very short diffusion distance to react with a red one, and therefore there is no need to grind. And this actually works every single time without failure, as long as you're at the right thermodynamic conditions, of course, and that you've given it long enough to react. Those are the only requirements. So this is, we call this, it's bake without the shake. Now, one of the things we did do, and this was published a while ago now, so I'm not going to dwell on it. This is a series of materials where these are the lanthanum nickelate series. These are mixed ion conductors, both oxygen and ion and electronic conductors. And these are notoriously difficult to make, particularly the 4310 or the 327. These take 14 days of heating and grinding some of these materials. What we showed was if you made an intimate mixture of lanthanum hydroxide or nickel hydroxide as a co-precipitate, as long as you were at the right temperature, and in this case, I've listed the thermodynamic temperatures at which this occurs. So if you're any higher or lower than that, you may not get the right phase for enough time. Now, some of these are taking 12 hours. And the reason they take 12 hours without any grinding, they take 12 hours because if you look at the structures of some of these lanthanum nickelates, they're quite complex, actually. They require quite a lot of organization. So in the first few hours, what's going on is some sort of structural reorganization. And eventually you see a very sudden change to the crystal structure. And we've looked at this with quite a lot of, in the past, we even went to the beamline to have a look at trying to identify when this change occurs and how fast it occurs. And it occurs within fractions, well, between measurements. So it's few seconds. So the complex structure of this is the fact that you've got N-perovskite layers with a rock salt layer in between. And this is essentially repeated. And this is the, this is the sort of complex structural organization. And this is why in this particular case, we probably picked the world's worst case, is the most difficult case ever. But the point is it takes a few hours and you don't have a choice in that because of this complex structure. And we're comparing the sort of time taken in solid and even in sol gel, which is supposed to be the ultimate process for homogeneous distribution of your elements, it still takes one grinding extra step with a lot of heat treatment taken. So that was an innovation. And what I've tried to do is summarize, if we think about time and temperature, we're doing solid state reactions. I'm going to put them into 4 categories. So at the top end, at the hottest end, this is temperature and this is time. So in the case of the lanthanum nickelates, it took 12 hours. You had no choice, or 6 hours, depending on the type of lanthanum nickelate, because of the structural complexity and the fact that these precursors were reacting, but then also rearranging to sort of form these structures. And so that's in hours. But the question is, are there opportunities in the minutes and the seconds range? If you have less complex structures, perhaps, or structures that don't mind being defective, the real opportunities for energy saving are going to be in the pink and the green. So if you could do something relatively low temperature and quickly, or even if it was a high temperature, but you could do it quickly, you could save on heat treatment time. So this would be a big energy saving. So I call this temporal solid state materials chemistry, and every material is different. The other innovation that I think our group is, I wouldn't say unique, but there aren't many groups that I know doing this. And that is in the use of, not only do we using continuous reactors to make initial precipitates, we're also now looking at how we can rapidly look at sort of flash heating. So the first thing is the static furnace. This is a small tube furnace in which we introduce samples and take them out again. So we call this static flash heating, okay? Because it's the furnace stays still, the sample goes in, it comes out. We have a procedure for that. And of course, you can vary the time and the temperature. After that, you've got a furnace where you introduce the powder at the top and you have an angle and it's rotating, and the material goes in at one end and comes out the other, and it might be in there for a few seconds. And you're trying to control the time and temperature based on the angle and other factors as well. It's quite complex. The third one is the large rotating tube furnace. So when we're trying to scale up, we need something that can make kilograms of heat treatment using our flash heating approach, which is flash generally just means it's going to be for a few seconds or minutes. Anything above about 10 minutes, I don't consider flash heating. So, you know, is this even possible? That was one question that we had. We started a big Innovate project a few years ago looking at this with LZO, lanthanum, lithium lanthanum zirconate, which is a solid state electrolyte. So I'm going to talk a bit about how we can achieve these solid state electrolytes using our approach. So I'm going to talk about approach number 3 now. So here we're making a precipitate of one or more metal oxides. They could be solid solutions, they could be mixtures of one or more solid solutions, but they might have up to 2 or 3 elements in there. And then we have the addition of some kind of lithium source. And you might say, why are you adding lithium here? And I'll save that for a question if somebody wants to really know. But we're adding something which is using incipient wetness. And incipient wetness is a process by which you are basically adding a liquid to containing some other metal ions like lithium hydroxide. You basically add the minimum volume of liquid you can to a certain given amount of powder. And the idea is that if you carefully dry that, the lithium hydroxide will be evenly mixed with your initial nanoprecipitate. I've shown it as a coating, and it is used for coatings as well. It's used for coating platinum onto catalyst supports, for example. The idea here is that you've got an intimate mixture between the green and the other oxides. And when you heat treat them, again, diffusion distances will be small, and that you'll get a really nice, efficient reaction without grinding. So here's the material. This is niobium-doped lithium lanthanum zirconate. So what we've got here is the lithium is added at this stage here by incipient wetness, but the elements of niobium, lanthanum, and zirconium, the 3 elements are added as initially from our solution and form a precipitate of our oxide or hydroxide. It doesn't really matter. So we take that mixture, and this one actually contains what looks like lanthanum hydroxide rods, and then some kind of solid solution of zirconium and niobium. It seems to be this is the preferred precipitation of this nanoprecipitate. And what you can see here, these rods are favored by this hydroxide structure. So we've added our lithium source via incipient wetness. And what we were able to do, and the target, and this was on a big Innovate project with Honda and Ilika, who are one of the leaders in solid state batteries. And what we were able to do was to make phase pure lithium lanthanum zirconate. But I want to tell you about the journey of how we did this, because I didn't even think it was possible, but they contacted us to see if we could come up with a new efficient way of doing this. So what we did was we made, and what I'm describing is a lot simpler than what actually happened, okay? So what we did was we made these nanoparticle slurries in our flow reactor containing these 3 elements. We added the lithium, so we cleaned them up, obviously, got rid of any residual ions. We added lithium, we freeze-dried that to distribute the lithium very evenly. And then we basically did a series of flash heat treatment experiments, a range of times and temperatures. So this is our design of experiments. It's a grid of time versus temperature. And on each time, we would put in the sample of our powder, lithium mixed with these oxides, put it in our static furnace, and then take it out again. And we do that for different times at different temperature settings for the furnace. And you keep doing that. I'm not sure why it keeps I'm still doing it. Okay. And what was really interesting was this, what we learned a lot. So at too low a temperature, this is what we call the Goldilocks experiment. You've just got to get the right time and temperature and everything clicks. Now, below 900 degrees C, at times of up to 30 minutes, the reaction either wasn't being completed. So there wasn't a completion of the solid state reaction. So we're using XRD, of course, to identify what's going on. Now we got incomplete reactions. So between 950 and 1000, across all temperatures and times, we got a complete reaction. But as you go to too hot, and this is where the Goldilocks bit comes in, I suppose, is at 1050, we're not seeing a complete reaction. And what's actually happening is lithium loss, the lithium precursor is volatile. And at higher temperatures, you start to get lithium loss from evaporation of the lithium precursor becomes competitive. And it actually means the reaction can't complete because you've lost too much lithium during the time that it's in there. Now, the critical thing for us is if we're going to scale this from a static furnace to a tube furnace, we ideally are only looking at a reaction time of 5 to 10 minutes. You can't really keep it in there much longer because it's a tube at an angle and the powder's kind of rolling down. So we were really looking for something that could be done in about 5 minutes. The other thing I'm going to add is that this powder is sitting in a crucible. and the crucible is not preheated. So once it goes in there, it starts to get warm, but it's not preheated in any way. Now, so what we then did was move to this continuous tube furnace, and this is where we put our powder in this time with the lithium precursor as well, and it's rotating. As you can see, oh, I was hoping the video would work. Okay, it worked earlier. So what we can see is that, first of all, the powder is now in direct contact with a hot tube. So this means you actually have to adjust the temperature slightly by a factor of about 50 degrees C. But once you do that, it works exactly the same. And this is some of the samples we made. It's about 5 kilogram delivery we did in the final phase of the project, where the other partners such as CPI were making inks of this for printable solid state batteries. And that was a number of people. I'll mention who they are and whose work it was at the end, and hopefully I won't miss anyone, but I will mention all these people at the end. So the key points here are that you're going essentially to under 10 minutes. By the way, the conventional synthesis of LLZO is usually, well, it's many hours and many heats and grinds, so it's probably more than 8 hours. I put 8 hours, probably because I just copied it from another slide, but it's a solid state reaction generally in industry. Obviously, the advantages here is this is highly scalable, and we were getting up to semi-kilos per day, or certainly kilos per day scale. And obviously, what you can do here is you can keep taking samples and monitor the quality of the material that's coming out through XRD, and that's what we were doing. And it's perfect for making printable inks because you're controlling the particle size to a degree, whereas when you use solid state chemistry, you're basically heating and grinding it, and it's very hard to control the morphology of the crystals. And in fact, what you're getting out is a very sort of jaggedy, broken up powder often, so it's not easy to disperse. So there's some big advantages there. Okay, so I want to just move on and talk about a recent paper that I saw that kind of interested me. So a lot of people, I've talked about the need to get rid of cobalt in NMC because of all sorts of issues of access of cobalt. And I've seen there's a lot of interest here in these high entropy materials, for example. So these sort of, nickel, manganese containing materials, and by doping in other elements. And there's been a lot of literature about, well, you can dope in elements to improve properties. Often if you're doping in something into say a cathode, such a nickel, manganese, cobalt layered cathode, sometimes these dopants can act as a pillaring effect and stabilize the structure, which means it's stable and doesn't form a rock salt structure, which is a less electroactive or not electroactive phase. So there's a lot of interest in doping, and when we started doing this, we started looking at, okay, let's look at a doping study using our process as a kind of validation. So again, it's the same process where we're adding lithium and we're heat treating. Now, in this first study, we actually looked at the effect of zirconia doping, and with our precipitation process, we're able to control the amount of each element that goes into the solution and therefore what's in the solid. So what we aim to do, and in hindsight, we probably should have changed the cobalt levels, not the manganese levels, but we basically replaced in a zirconia, what we call NMC, nickel, manganese, cobalt, with 80% nickel and 10% of both manganese and cobalt. So here's the 100% in terms of element composition. And what we're doing is replacing about the 10% of manganese with up to about 4% of zirconia in its place, which is this purple bars. So what we're showing you is this is the actual elemental composition. We had a fairly good control of the composition, and these are actually real values that we obtained. And what we have sort of developed is the ability to, so these are the different, so I'll just explain these diagrams. This is the percentage of zirconium doping up to about 4%. And this is the heat treatment temperature that we use. And it would have been for a standard number of hours. I don't remember how much, probably about 3 hours or something. Because at this stage, we were just looking at sort of one heat treatment to sort of get an idea of capacity values. And the way that I find much easier to look at large amounts of data is to use these heat maps, where red means it's hot, and obviously this is suggesting that there's a high capacity. And if you're familiar with battery terminology, this C rate tells you how fast the battery was charged or discharged. So a 1C is a 1 hour charge or discharge. Anything less than a 1C, so these three values are less than 1C, these would be fractions, so multiple hours. So for example, C over 10 would be 10 hours, and C over 20 would be 20 hours, I guess. Okay, so, and at those charge or discharge rates, what we can see is that at the very slow charge or discharge, C over 20, it turns out that the 1.35 in fact, across all three of these slow charge and discharge rates, is giving the highest capacity across. So it's a sort of like a hotspot thing. And that's very interesting. What we're very interested in is actually the higher power, which is at higher C rate. So this is 2C. So 2C would be half of 1 hour, so 30 minutes. And for example, we're going to see 10C in a minute. 10C would be 6 minutes. So it's 60 divided by 10, which is 6 minutes. So as we charge and discharge much quicker, it turns out that the champion sample is the 0.57% zirconia doped NMC material, which is of course replacing the manganese, I should say. So this is, what we're trying to do here is identify which is the best sample for high C rates. And the next step really is to try and engineer the electrode to make it more conductive and perform better. So this was our kind of next step. So I'll just sort of highlight those points. So one of the things we started to do was replace in our electrode, often you're working with 80% weight percent active, 10% binder, and 10% of carbon black. One of the things we started to do with our cathode materials was to start to look at replacing them with conductive carbon nanotubes. So this is one of those experiments. And what I'm showing here is this is for the 0.57% zirconia dopant, which was the champion sample in the last slide. So we took that material and then we started to play with it. And what we've done here is actually looked at the capacity values. So these numbers in the boxes are the capacity values, the hottest being the red one. And as we add, so what we're doing is replacing that 10 weight percent of carbon black with up to 100% replacement of that 10% with carbon nanotubes. And what you essentially find is what you might expect, that as you add more carbon nanotubes, it seems to improve the performance, or you reach a limit. So at about 75% of carbon nanotube replacing, so you've got 25% of carbon black as a percentage of the, the 80-10-10. It's that 10% that your 75% is of. You find you're reaching the optimum, and if you add more, it actually doesn't make it any better, or maybe even makes it slightly worse. So at 10C, for a 6-minute charge and discharge, for essentially an 811 NMC material with a bit of dopant, we're getting really good performance. And if you don't add the carbon nanotubes, it pretty much dies a death. You can see here, you're at 5C and 10C, you don't record anything here, so it just drops off the cliff. Now, this is an 80% active material. Most battery companies are interested in much higher than that. They want 90 or 95% active material, but it means you're generally adding less conductive. So we also looked at the possibility of adding 90% active material. And here's the data for that. And this is just a selection of data. And what you can see is that when you add the optimum amount of carbon nanotubes, I'll refer you to, in particular, to the 80% comparison. And this is our zirconium NMC with a 0.57% optimized with carbon nanotube, and then the 90%. It's the blue and the green respectively. So what you can see is that obviously as you go from the 80% to the 90%, there is a drop off in performance. And I'm sure there's more optimization we could do. And you can compare this to the tar gray with carbon black, or some of the other materials, the same materials with carbon black at 80 and 90. They definitely perform worse. And so really this is promising for capacity retention and perhaps reducing degradation as well, because of the efficiencies. Okay, I'm just going to move on to the last bit. This is probably the bit, well, this is the bit that I think is probably one of the most exciting things we're working on. And we filed a patent as well recently, Shutao Wang, Tom Ashton and myself, early 2022. And we're still working on this quite a bit. So I'll just give you some initial results of what we're doing. So this all started when we were on another Innovate project with Kinetic, and we were basically tasked to scale up the cathode synthesis. And the truth is we were really struggling. We're struggling to do that in a batch furnace. And we realized that we couldn't really match the commercial material or get even close to it. So the project was about high power cathodes, so cathodes you can charge and discharge really quick. And towards the end of that project, we were really struggling. And towards the end of that project, we started getting a bit desperate, to be honest. And I started thinking about the idea of, because we had this other project looking at flash heating for the LLZO, and I started thinking about whether there was any way we could actually make, and everything in the literature tells you that's a bad idea, making cathodes in flash but with a short heat treatment time. And the reason is, in solid state electrolytes, it's okay to have a defective solid state electrolyte because that's how lithium ion diffusion works well when you've got a very defective structure. But in cathodes, the general consensus is it's a layered material. You don't want to have defects in there, certain types of defects, because they block lithium ion diffusion. And it's generally considered a really bad idea. Well, actually, it turns out that's not true, thankfully for me. And we now have a current Faraday project, which is taking this up and scaling what we've achieved. And I'll tell you about it. So what we were doing was taking these nickel manganese cobalt materials, or nickel cobalt alumina MCA. These are high power cathodes. And essentially we were mixing them with lithium again. And then we were doing flash heat treatment, and we were doing XRD data. And what we were trying to look at was a particular thing. So one of the things was, is it phase pure? So this is actually an experiment where we're looking at temperature. And what I'm actually plotting in this, what we've plotted here, is the peak ratio of the 003 to 104. Now, this peak ratio is often considered in the X-ray diffraction pattern as being a good indicator of whether you've got low cation mixing. And what I really mean by that is you've got this layered structure with your nickel manganese cobalt in the blocks, and then between the blocks you've got these lithium ions that can diffuse. And often you'll get a nickel and a lithium swapping places, and that means that the lithium, you've got a defect where a lithium's stuck in a nickel position, or you've got obviously the reverse of that, where the nickel's stuck in a lithium position between the layers. And it's generally considered that if you look at the XRD as a kind of a sort of weather vane, you can sort of see that these two peak intensities, if they're around about 1.2, and again, this is very waving in the air. I mean, generally that if you get a value near 1.2, this is considered to probably give you a good cathode, and you'll get low cation mixing. And that's generally what people believe is the kind of way to screen these materials rather than testing every single material. So we're very interested in, is it phase pure? And the work of Tom Ashton, who's been brilliant on this, is trying to look at sort of the amount of weighted defects in the structure using XRD and Rietveld refinement of XRD data. And it's giving us an indication of whether a material's got a lot of defects in it or not. It's not a perfect process, but it certainly gives us a feel of what's going on. And so what we've done is here, from the XRD data, we at different times and temperatures, there's 900 degrees C for 2.5 minutes, using our flash furnace, 30 minutes up to 120 minutes. We've been just looking at the values, and anything near about 1.2 is red. Okay, so as you get further away from 1.2, it's more green or other colors or brown. So when you're looking at this, you can see it appears, well, you've got something interesting at 2.5 minutes. But frankly, I mean, I'm not saying this is particularly useful unless you actually test the batteries of these materials, is what we actually do. And what Tom was finding in particular when he was looking at some of the Rietveld refinement, and this is on the NCA material, was that in the initial few minutes, as you're heating up these materials, often you'll see what looks like some very disordered structures, maybe more than one disordered phase, which are distinctly different enough that you can separate them in the XRD data. But as that develops, you essentially just see one single disordered phase. And what Tom has been trying to do is to sort of weight the total amount of defects by these contributing phases or the single phase, and trying to plot that. And what we've been doing is measuring the capacity of these batteries in the normal way. So this is a sort of map of the weighted disorder. And by the way, I should say, most people believe that when you make an NMC cathode, you're going to heat treat for 8 hours, and after 8 or 12 hours, and after that time, you're going to get to a weighted, total amount of weighted disorder of around about, well, below 5%, typically 2%. And that generally means that you've got this wonderful idealized structure where the lithium is all in between there, and that you've got very little of the lithium on the nickel side, or the nickel on the lithium side. I should say that's because they're of similar size. I think it was nickel 3+, which is a similar size to lithium plus. So anyway, so just to finish this story off, what we're seeing here during these times and temperatures is much, much higher than you would expect for a good performing cathode. And this is what the whole of the literature is pretty much saying, with a few exceptions. So I'm going to talk you through what we've observed. And this is for NMC 523. So this will be 50% nickel, manganese 20%, 30% cobalt. And this is, again, one of the sort of interesting cathode materials that people are very focused on around. And the 622 as well are very much of interest for automotive, as well as the 811. So what we've plotted here is capacity values, and this is at a 10C. So this is a 6-minute charge or discharge. So anything near 100 is very, very good. Okay. So that's the capacity values in red. The blue is the total weighted disorder as calculated from the, as I described earlier. So this is in this column, we can see the capacity, we can see the weighted disorder, and I guess the colors, again, what's the relevance is the high capacity is red. In this case, I guess the low weighted disorder is more redder because the suggestion is that low weighted disorder is somehow better. Well, it turns out it's not. And then on this column, we're again plotting that ratio of those XRD peaks, 0.03 to 104 intensity ratios, and anything near 1.2, which is what people think is good, is what we've plotted here. So the truth is none of this really makes any sense. But what does make sense is, and this is the time that we heat treat these for. So what we've done is we've plotted time on the bottom axis. And what we're really looking for, where's the best capacity and what is the total weighted disorder in that material. And what it turns out, if you sort of roughly plot this weighted disorder thing, you see this increase up to above 20%, and it goes down again and up again and down again. And eventually, if you were to run this for 8 hours, the material would probably give you a capacity similar to our capacity after about 2.5 minutes. So at 2.5 minutes, we have a material, and if we just go down to this point here, it has a weighted disorder of above 10%. So it's quite a disordered material. It's certainly not near 2%, and it has a capacity value that is probably comparable or better in some cases than the commercial equivalent material. And I'll give you some results here with NCA. So again, I'm not going to talk about weighted disorder on this slide. I'm just going to focus on the actual capacity values. So one of the things that we are currently working on in our Faraday project, it's a seed project that lasts a year, is we're looking at the static furnace. So this is data from the static furnace. So this is at the different C rates. And at 10C, 128 milliamp hours per gram in a 6-minute charge or discharge for an NCA material is 10% better than the commercial NCA material that you can buy, that our industry collaborators can get. 10% is a big deal at 10C. So now our job is to take it from the static to the small rotating to the large. So we're on that journey. Here's some early results at a specific temperature, because I haven't mentioned the temperature here. And what we can see is that the first experiments that we're doing on that, we're getting ballpark in the same region. And remember, this is the powder is in direct contact with the tube here, whereas it's not directly in contact with the tube. So that's why there's a difference between the values at 10C, but we are ballpark getting near to our target. So I'm very excited about that. And I think between now and January, there's a big job to be done there. Tom's also doing a lot of other things parallel. He's looking at working with various beamlines in the States and people here. And Alex Retty is now joined, and we are looking at PDF data for X-ray and neutron data to try and model what's going on in the first few minutes, because what we did do was take data from sort of 2 minutes upwards to the optimum and try and see subtly how the material is changing. And I'm looking forward to finding out more about that from that. So the key points here is that every NMC, in fact, we've done this with other NMCs, we've done it with 111 and 622. Every NMC or NCA material has its optimum time and temperature, and it's usually under 10 minutes. It is under 10 minutes in every single case, which is what our patent is covering. It also works with sodium ion chemistry, and it probably will work with a whole load of other chemistries where you can do a conversion from a bottom-up precursor in seconds or minutes. It works with other stuff, but I can't talk about that because we might file a patent on it. But the point is, it's orders of magnitude less energy in terms of time spent in the furnace. I think the ability to put materials in and quench them by taking them rapidly out allows us to freeze in the structure of the material at a specific point, which gives us that understanding of how it changes the properties and how the defects change. So this is a very consistent process. I'll just finish because I'm out of time. Really, where is this going? Well, we put in a massive program grant, which didn't get funded, unfortunately, this year. One of our aims was to be able to take all of this data and really work with machine learning to allow us to understand how performance of the materials can be integrated with machine learning and modeling, of course, as well. So people like Furio Cora were also part of this. And yeah, unfortunately, that didn't get funded, but I'm very optimistic that, really for us, this has got to be of use to industry. The discovery of these materials and the improvement of the timelines to get from ideas to products and then scale up is what we're about. And I think this is definitely the way to go. And I hope some of that AI money starts to come towards the right places in materials. So overall, the key thing is that the intimacy of mixing at the nano level allows us to make materials that are very well defined. So it's a bit like the sort of, it's our go-to process. We actually have developed another process which isn't continuous hydrothermal, but it's continuous, and it seems to perform just as well in some of the early examples we've done. So for example, we can now make LOZO using a completely different process at room temperature because of the understanding that we gained from using the continuous hydrothermal materials, because they were very intimately mixed, and that was really important. I'm also talking to people about the idea of recycling waste streams and actually using them, because of course we're making things from solution. So is there a possibility there? And I'm going to have those conversations in the coming days. What I've spoken about is the key thing is overcoming mass transfer limitations with that, not having extra steps in grinding that can induce impurities. And, it really is possible to make materials now using orders of magnitude less energy. And I think the key future is going to be integrating this machine learning in materials. So thank you very much for your time. I'd like to thank the sponsors. I'd particularly like to thank Carlos, Lynn, Daniel, Shutao, and Tom, who've worked on most of the stuff I've described today. If I missed anybody off, my apologies. I'd like to thank the sponsors, in particular Ilika, who approached me, and I'm really grateful for that, and Kinetic, who have worked closely with us, and I think we're going to be moving forward with them quite in a big way, which we'll announce in due course, hopefully. And thank you very much for listening, and happy to take some questions. Okay, I haven't been seeing the chat, so I don't know if anyone had any questions. Oh, there's some questions. Okay. Right, so if you do want to put some questions, please feel free to type something into the chat box or the Q&A box. Actually, let's do the Q&A. So I only see one question, so I'll just answer that. And if somebody wants to ask a question verbally, I'll just unmute you if you just indicate in the chat all the questions. Why did they select zirconium to be doped combined with, okay, yeah, instead of other elements? Okay, yep. Yeah, okay, right, great question. And if I knew the answer to that, I would, Alexa off. Tell me about my next meeting. So first thing is that there was some literature background saying zirconia doping can improve. First thing is NMC811 is notoriously unstable in terms of, if you leave it lying around, it goes off. Everybody's interested in it because of high nickel, but they know that you need to do something with it. So generally what people are doing is they're coating it. They're coating the surface to protect it with something that will be more stable. And usually it's a lithium-ion conductor. So the nice thing about certain things that you can put on the surface, they can form a lithium lithiated species, which kind of acts as a reservoir for lithium and a sort of protection as well. So zirconia is one of those elements. You can sort of form lithiated species, but of course we're not coating. So what we are doing is doping, and it goes back to what I said about the layered structure. Okay, so this layered structure, what some people believe is that the zirconia, because it's not electroactive, okay, so it basically will just stay where it is, and what they believe is it acts in a sort of pillaring, if you've got these sheets, and it basically acts as pillars to stop the sheets from breaking apart or from degrading. Because often what happens is that process will lead to the formation of rock salt, which is lesser electroactive. Well, I don't think it's electroactive at all, unless it's highly distorted. And so zirconia doping seems to stop that degradation pathway, that transformation of structure to rock salt. So there is a bit of literature on it. It's not electroactive, and so it has that effect. Now, why that amount of zirconia is optimum, I don't really know. But what we do know is, at the higher levels of zirconia above 0.57, it's certainly you are getting it on the surface because it's not soluble in NMC. So we see that clearly from the XRD data. So there it could be having a coating effect possibly, but we're not trying to coat it per se. We're just trying to dope it. So I hope that explains the question. I don't know if anyone else wants to ask a question. Oh, they've got a hand up from Sanka. So I'm going to let you chat. Allowed to talk. Sanka? Oh, let me just see if we can. Allowed to talk. Okay, Sanka, you should be able to talk now.
Can you hear me?
Yes.
Yeah, great. Excellent talk, Jawwad. It's really interesting. How do you compare it with flash spray pyrolysis, or the kind of methods very similar to what you're talking about, the short heating time, and also Ivan's previous work on this self-propagating heating systems as well?
Yeah, that's a good. So the thing about flame spray pyrolysis type techniques, I guess my comment would be that you're generally require some kind of solution and some special precursors sometimes, which have to be exothermic, given, I mean, the flame's hot, and maybe as much as, I don't know, 1500, some of these things are probably even hotter than that. So the thing about spray pyrolysis, it will convert the material in solution to a solid product. So it's particularly good for things like lithium iron phosphate, where it just produces lithium iron phosphate, and that's been done for a long time. The issue is, if you want to control the defect chemistry like I showed you could do with NMC, and this is the first time I've spoken about this publicly, it's going to be really hard to do that with a flame. A, because the temperature is so high, so everything's going to go really, really quick. To dial in that level of detail on the defects and systematically measure it, I think it would be really difficult. Probably because the temperature is just so high, and it doesn't allow you to control the defects, I would suggest. So I think that's why it differs. I mean, in a way, what we're trying to do is build up understanding. So it may be that somebody could take what we've done and use a completely different process and achieve an optimum defect concentration that gives really good performance. I should say this also is, so far we've looked at stability studies, and it actually seems to be stable. One of my concerns was, do these defects kind of iron themselves out with cycling? And it doesn't appear they are degradative, but there's more work to be done to prove that. Thanks for the question, Sanka. I don't know if you have any other questions, but that was a great question. Thank you. Oh, you asked about the self-propagating thing. Again, I think that's about control, isn't it? I mean, because that self-propagating heating thing is like, that's so fast. And control is what it's about. For us, it's always about control. Control of the elemental mixing, and control by flash heating to build these maps of time versus temperature. And I think that's how knowledge is acquired. And the beauty is there's a lot of opportunity there for modelers and also for machine learning people to sort of try and understand better about creating models that might help us to explain why this is working. And obviously, I mean, there's a huge, this data, I mean, I'm doing some collaborations with people who can take the data and hopefully, so we've got a few machine learning students who are going to have a play with it. So we'll see where that goes. Andy Beale has a quick question. So thank you, Andy. How does the crystallite side vary with flash heating? Or perhaps the question should be, how much of disorder are you seeing to be attributed to different? Okay, that's a killer question, that is. The answer is I was thinking the same thing this morning. And when one of the things, so we've got on the 11th of November, we've got our next meeting, and we're going to actually be deconvoluting the changes in crystallite size with in the PDF data for the neutron work. And this with a guy called Tucker in the States at one of the beamlines, Matthew Tucker. So I think I'll know about the 11th of November. Tom will have had that meeting, and we will have a bit more of an idea of that. I think what's important for NCA is the particle size is significantly smaller than it would be for a commercial NCA, because that one of the beauties is that by doing this bottom-up approach and the flash heating, when you talk about high power, people generally want smaller crystallites, although you might say, well, there's a trade-off between SCI. If you've got high surface area, there's a trade-off. We're still talking in the microns, maybe 3 microns. So I don't know the answer, but that's an absolute killer key question, and we are aware of the fact that it could be down to crystallite size as just affecting the rate performance. But we'll see. I mean, and if it's just out of crystallite size, well, that's a great story anyway. So, but I think the disorder thing cannot be ignored. because given what everybody in the literature has been saying, I think there's a few modeling papers where they talk about, oh, well, if you had this disorder, you could get superior lithium ion diffusion. And if you think about it intuitively, yeah, if you've got a certain amount of disorder, you might be able to get other pathways. So I've seen papers where they talk about in a 2D diffusion material that maybe there's a third dimension that can be accessed because of these excessive or significant amounts of defects above 2%. So maybe that's another thing. Well, we still can't ignore the defects. They definitely play a role. But yeah, point taken, and a very good point taken. So we're getting to 53 minutes past. I don't see any more questions. I don't know if anyone has any more, but oh,
sorry.
You again, Sanko, is it you?
Yes,
Okay.
if you don't mind, one more quick question.
Go for it, mate.
You know, you do a lot of engineering stuff. Is there a way you need to put certain amount of material into the flowing furnace? Or can I say I put a half a gram at a time or a 10 milligram at a time? Is there a control that is required in terms of allowing it to get the maximum heat efficiency?
Okay, so the main thing is that when you're in direct contact with the furnace, you can pretty much assume that there's no heat transfer is not a problem. Whereas for the static furnace, there is a sort of slight issue with heat transfer, you could argue, but it's convenient. So we use that first. The small rotating tube furnaces, we've just started playing with. I mean, we've had them for a year or so, but we've really just started to play with them now because of this Faraday project. I think they're ideal for some. So right now, we have a new student called Bangsheng. Bangsheng's going to be playing around with the small static furnaces as well as Tom, and looking at how reliable they are, because the key thing is the time in that, you know, the temperature, but controlling the reliability of time spent in that furnace is a slight smearing out. The chances are some of the powder will stay slightly longer. So I think the way to go, if you've got small amounts, is just go with a small static, or if you've got slightly more, maybe a few grams, you could play around with the rotating tube furnace. But there's another piece of kit that I didn't talk about. And I had in my mind that what would be great if we could have a conveyor belt furnace where stuff just comes along on a belt and it passes through exactly an amount of time. You can put as little as you want in or as much as you want, because we just work with 1 gram or so because it allows us to make a coin cell. And it turns out there's a machine that was sold years ago and you can't buy them now. But I found it turns out Kinetic have got one. It's called a DEC 840. If you Google DEC 840 thermal furnace, it's basically a steel mesh furnace going into a tube, and it basically the material passes through and comes out the other end. So the nice thing about that is that, okay, it's a bit like the static furnace, but it's kind of continuous. So that's another furnace we're going to be playing with soon. But I still say that if you've got like a gram or so, play with either the static or the I would say play with the small rotating tube furnace, Sanka. Yeah. Cool. Right. Thank you so much.